Well, now that we have the power rule, of course we want to take derivatives of more than just monomials. We want to take derivatives of any kind of polynomials. But for that we need a couple other rules as well. And the first one is the constant multiple rule, which is very easy to understand and also to prove. What it's saying is that a constant doesn't really do anything with respect to the derivative. You can just pull it out. Okay? So we can just check this very quickly with our definition of the derivative. If I want to take the derivative of c times f of x, all I'm going to do is put c times f of x into my difference quotient, and you can see c just sits there, right? It's c times f of x plus h minus c times f of x all over h. Well, so I've got a c in both things on the top, right? So I can pull it out. But actually, I can in fact pull it all the way out. I can pull it out in front of the limit because the limit is over h. It doesn't say anything about c. So I just pull it out, and then I have c times the limit of my ordinary difference quotient, which is just c times the derivative, which is what I was trying to prove. Okay, so pretty straightforward. And then the second rule, it's actually two rules, sum and difference rule, but I'm putting them together just because it's easier to remember it. One, difference rule. And that's going to tell me that the derivative of f plus g is the derivative of f plus the derivative of g. Okay? So, which is great. Very easy also to prove. So we'll go through that real quick, just so you have some idea. And okay, I said difference as well. This is also true if it's a subtraction. Okay, but I'm going to prove the one with a plus. So what do I mean by the derivative of f plus g? Well, first of all, what is that? F plus g of x, we know what that is. It's just f of x plus g of x. So if I'm going to put that into here, I hope I have enough space, right? I'm going to have f of x plus h plus g of x plus h minus f of x plus g of x all over h. So all I have to do is rearrange my terms. I'm going to put it over here so I have a little more space. I'm going to put the f's together and the g's together. F of x plus h minus f of x plus g of x plus h minus g of x, right? And then I break this up into two difference quotients because you know you can do that as long as, of course, all these things are going to work out. In other words, these derivatives exist. Right? And then this is just what I wanted, the derivative of f plus the derivative of g. And if it was a minus here, there would be a minus here and a minus there. So you could work it, if you worked it all out, you'd just have a minus there. So it's the same proof. Anyhow, so what am I going to do with those? What's nice is that now that I have this, and let me just throw it down here, our power rule, which is that the derivative of x to the n is nx to the n minus 1. Well, I can take the derivative of all kinds of stuff. For example, I have one here somewhere. Oh, yeah. I want to mention something before I go on. Just briefly, this works for sums and differences. It does not work for multiplication. So the derivative of f times g is not equal to the derivative of f times the derivative of g. Okay? And this is, of course, because when I'm taking the derivative, I've got that whole expression that I just erased. And even though I can move it around with addition and subtraction, when I try to do it for multiplication, things don't work out right. In the next section, which is 3.2, we'll learn how to take the derivative of one of these things. We need the product rule, and it's more complicated than this. So that's just a heads up. But we shouldn't need that for any of the problems in this section. For example, if I just take any kind of old polynomial here, and I really just made this up, okay, whatever polynomial. You can imagine that trying to do this with the difference quotient would be an absolute headache and very difficult, but we can go ahead. And so this first time, I'm actually going to write it out a little bit, putting the derivative through here. So df dx, but not all the way. Like I know I can pull out the constant and pull out the pluses. So all I have to do is write it like this. And then each of those derivatives is just the derivative of one of these, power rules. Minus 12 times the derivative of x, except for this last one, which is derivative of a constant. Okay, so I go through and do those, and I've got 4 times 10x to the 9th minus 6 times 8x to the 7th plus 13 times, 4x cubed minus 12 times 1 plus 0, right? Because derivative of constant is 0. Okay, so there's my derivative. So I can then use this as well, let me get rid of these guys, to answer whatever questions. So if they ask me to find the tangent line to f of x at x equals 1, now this is a lot easier, right? Because I know what the derivative is here, so I can figure out what the slope of the tangent line is. I'm just going to put in 1 here. So here's df dx is this thing. Now the slope is going to be df dx since I'm using that notation. So I'm just going to try to stick with that notation for this problem. Oh, you could have changed to f prime, doesn't matter. At x equals 1, so I just put in x equals 1. So what do I have? 40 minus 48 plus 52 minus 12. So 40 minus 8. So it's 32. Okay? So that's going to be the slope of my line. And then I need the point. Sometimes they'll give you, like both will give you the x and the y coordinates. Here they only gave me the x coordinate. I do have to figure out the y coordinate. Easy enough. I just put it back in my function, right, because y equals f of x. So I'm going to put this 1 into here now as well to figure out my y coordinate of my point. 4 minus 6 plus 13 minus 12 plus 9. So what do I have? Minus 2 minus 1 plus 9, so 6. Okay? So then I want a line of slope 32 going through the point 1, 6, right? So I get y minus 6 is 32 times x minus 1. And then I have 32x minus 32 plus 6. So what is that, 28? Minus. Yeah. Okay. 32 minus 6 is 28. All right. So there you have it. Now we can work with more complicated functions because we can take the derivative in an easier way.